Hello everyone, welcome to the probability series. So last time we have talked about continuous random variable. So this class we'll talk about is first there's two topics. First there's transformation of random variables and also the continuous versions of expectations and variance of random variables. So first let's see one example. So here, N01, this character means it's a normal distribution with mean 0 and variance 1 or standard deviation 1. So this is the first distribution we see. And this is a Gaussian distribution based on the shape. And y is equal to s squared. And this is another random variable. So in this case, we can see it as like y is a transformation of x. We add a new function to it. It's like x squared. So this is already a transformation. So after we knowing the PDF of x and its transformation, we can find the PDF of y. This is one example of the transformation. So let's see the PDF of the standard normal distribution is this one for all x in R. And so we can say its CDF. Its CDF is just computed by adding an integral on it. So this is the PDF. P and the x smaller or equal to x. X is a realization, and in this case, it's a variable, and x is the random variable. So we know it's PDF and it's CDF, and we can use this two information to find if y is equal to x squared. So first, let's compute if y is smaller or equal to y. This is equal to 0 because if y is smaller than 0, let's see what will happen. If y is smaller than 0, x squared is smaller than 0, but x squared is a positive number. So in this case, its probability is 0 for y smaller or equal to 0. And so otherwise, if y is greater than 0, then it's not 0. Then it has some values based on the infinite property of PDF of the normal distribution. So let's compute that one. So first we'll do a change of variables in the transformation. Let's denote y equal to x squared. So y smaller equal to y, the capital Y smaller equal to smaller y is equal to the probability of x squared smaller than smaller or equal to y. This makes sense because we're just doing the transition of variables. We just change it from here to here. But in the next step, some interesting thing might happen. It is we are actually solving this inequality for getting rid of a square, or we do the root square computation. So it becomes negative root square y smaller or equal to x smaller or equal to a root square y. So this is the how to say the CDF of y, because we're computing as if all of the probability add up to the y condition. That is all of the probability smaller or equal to y. All right, so this is CDF. And how can do that? Well, because we already know x, we are just changing y to x, and we know the PDF at x. We know it here. So we can compute it as the integral from negative root square y to root square y. And we plug in as PDF in the middle, and then we do computation. And as soon as we are finding out this equation, we can do one more step. Which is to separate into two normal CDF, which is from negative infinite to root square y for the upper bound, and from negative infinite to negative root square y, which is the lower bound. So if we minus the upper bound by the lower bound, both growth from the negative infinity, then it becomes like two CDF minus each other. So we got CDF here. So it's just like root square y minus negative root square y by using CDF abbreviation. Okay, after we know the CDF, we are computing the PDF. So PDF is just like the derivative of CDF in most cases. So we're doing a differentiation here. So we compute the differentiation of the CDF we just found. Um, notice that we can use the chain rule here. So this is the we first compute is the overall this function's differentiation, which is phi root square y, and we do and we times the differentiation inside, which is this is what 1/2 1/2 yeah, so it becomes becomes -1/2, which is root square y under 1, and we times its power, which is 2 under 1. So it becomes this form. And similarly, we can compute the lead form. And luckily, we find out because it's a symmetricity of the normal random variable, we can compute the phi x equal to phi negative x for all x. So this one equal to this one. So we just add two of them together, cancel out the negative in these two forms. So it becomes this one. The 2 under 1 is cancelled. And if we want to write in a more formal form, we can write it in this form by expanding the term out. Okay, so this is roughly we're computing example of transformation. As we can see, I think the most difficult part in this problem is this part is to change x from y. And we also notice this is only for y greater than 0, so its domain is not a real line. So we need to separate what's 0 on the interval, like that one and this one. So if y is smaller or equal to 0, then its PDF becomes 0. All right, we can see another example here. We can see another example. So last one is a normal distribution, standard normal, and this one will be a uniform distribution. And we change the transformation into y equal to 1/x. So it seems like a big change, but logically it's very similar. So we can compute in this way. So if we want to find the PDF of y, we first find the CDF of y. So it's like p y smaller or equal to y, and in this case, change variable. Remember, we changed this to x squared last time, so this time we change to 1/x. 1/x smaller or equal to y. 1 over this is equal to just time, like you can first times both sides with x, so 1 smaller or equal to xy, and then divided by y, so it becomes like 1/y smaller or equal to x. And because we know the x distribution, we want x to be a random variable. So in this case, it's equal to 1 minus p x smaller or equal to y over y. Why is correct? First of all, we change the direction of the inequality, so the probability will be 1 minus. That's intuitive, or we can use the formula theorem we studied before. And also another thing is like why this is smaller equal, why we can still use smaller equal, not like a smaller here. This is because equal is just a 0 probability based on the PDF's definition. Okay, so after we can compute this is equal to the CDF of x 1/y. And we just do one step abbreviation. It becomes 1 minus 1/y. So a y from this step to this step is true. Because remember CDF is the CDF is a uniform distribution, which means it's flat. It's very flat across the from 0 to 1. So if it's smaller than 1/y, what happened? What happened is it just goes from 0 to 1/y, distance divided by 1 minus 0, so it's just 1/y. So that's why we get this result. And this is only for y greater than 1. So imagine if y is smaller than 1, what happened? This means like y is greater, y will be greater than 1, right? So y greater than 1, what happened? It's like it go beyond the definition of the uniform distribution. So y is actually uh undefined, because you say y greater than 1, x x smaller than 1. So yeah, so you just like it's go beyond the 1 0 and 1 interval. Okay, after we find the CDF, we do the differentiation to get PDF, which is very similar as we did before. So y greater than 1, we get this one. 1 smaller equal to 1, 0 divided by 0 is still 0. All right. So for these two examples, hope you get a clear idea of how transformation works. So for the next one, we are doing we'll give you a theorem about transformation of PDFs for continuous random variable. So this is a fundamental theorem we'll use. Remember, remember, as we did problem before, we don't use any theorem. We're just computing by our mind, our thinking. So, but if we meet a difficult problem that is not very obvious how to do the transformation, we can use the formula. So the formula is very clear. So if x is a random variable with values in I and the PDF fx. So what's that mean is, well, x is defined on I. So it might define on R, but it might not define on R. For example, x squared is not defined, it's not defined on R. Or maybe this is not a wrong example because x squared is not a random variable. So say, yeah, like the uniform distribution, like the I is in 0 and 1, so it's not R. So that would be a right example. Okay, and there's one transformation we denoted by U. U goes to from I to J. So last example here, you can say I is 0, 1, and Y, and what's Y? And maybe we see this one. Yeah, X is 0, 1, and Y is, yeah, Y is from so this is I, and Y, because it's from 0 to 1, so this becomes 1 to infinity. Yeah, so this is from 1 to infinity. So this one is this is the J. J is 1 from infinity. So this is J. U is from defined from I to J. And U inverse U are both continuously differentiable on I and J. So so the new random variable we denote as a transformation from original random variable. So its PDF becomes, it's not in J, like last example, it's not from 1 to infinity, it's smaller than 1, then it's 0. Otherwise, it becomes this form. So is this form just as we computed in last question? This is a very good question to ask. So before, let's say what's U inverse. U inverse, yeah, U inverse is same because you put yeah, as this step, the two steps illustrate at the beginning. So 1 over x smaller equal to y is 1 over y smaller equal to x. So it's still 1 over x. Oh no, 1 over y. So yeah, it's still 1 over y. So 1 over y, we do differentiations 1 over y squared positive if we take the absolute value. So what's that one? Well, because it's like uh because fx x is a uniform distribution, so it's okay. So this one, it's slope is 1. So slope 1 means the differentiation is also 1. So this is just 1 over y squared. So it's this one. And for for that one because beyond scope, so 0. Okay, so what's the idea? What's the real idea of transformation? It's like we do a very slightly move from 0, from x0 to x0 plus like the delta x, which is a very small increase of x. And after we apply u, it becomes this part. So it's y0 plus a slight move of delta 1. All right. So this is a probability from x0 to x0 plus delta x. And after transformation, it becomes y0 to y0 plus delta x. And how to understand this one? It's like if the delta x goes to 0, then and this region becomes really narrow. It's narrowed down, so we can see how the probability change for each spot x0 on the continuous random variable. Okay, and if you want to give a proof of why this is true, let's talk about it. So y0, or we just for abbreviation we'll use the y instead of y0. Okay, so first we do the PDF of y. It's 1 over the delta y, because delta y is the like the estimated region over the probability. Okay, so 1 over delta y times probability from y to y plus delta y, which is small increase on that. It's very intuitive, and y is equal to ux, and we do a functional wise computation. We do the functional wise times, or we can say we do a composition functions. We compensate with all of them with u inverse. Then it's u inverse y small equal to x small or equal to y u inverse y plus delta y. Okay, and the next step is very critical. It's like separating the fx out. So in this case, because it's like this form is look like how do you say, look like a CDF, and the CDF is the differentiation of PDF. No, CDF is an integral of PDF. So if we want to get a PDF from CDF, we do the differentiation. So we differentiate this form to get rid of P. So the PDF becomes in the front, which is y0 or y, and this part is we use this one to minus this one to compute the derivative, and this part remains to be here. Okay, so what's this? Let's see what's this. This becomes the y plus delta y minus minus y, both in the function of u inverse, and this looks very very likely to be a differentiation of the function of u inverse, because this is like y plus delta y minus y. So this is a absolute value of u inverse differentiation. So get this result. And how we can, and another things, if we can find out the transformation PDF, we can use it to find its CDF as well, which is do a integration on it. All right, so the PDF, the CDF of something, this is a collection of CDF, like it's like B, it's like a CDF of B minus CDF of A. So this is actually an operation on the CDF, but we can still do it. So how we do it is we go from the U inverse A to U inverse B integral over the PDF we just calculated, and find out this form. And this will be we can use this formula, this integration, to calculate the CDF of a transformation over x by function u. All right. So this example is like a computing of random variables of transformation using theorem 7.4, which is this theorem. So after we introduce it, we'll actually use it to solve it to find out if it's actually working or even more difficult by our thinking at the beginning. So let's see the same example. X is uniform distributed from 0 to 1, and y is 1 over x. So in this case, let's say y is equal to ux and is equal to 1 over x. And u minus 1, y is 1 over x. That's right. That's right. Inverse is this one. And so let's see the formula. What we will compute. First, we'll compute it, the transformations inverse differentiation. And we also need to compute the PDF of the inverse form. Okay, so let's first do the differentiation. Differentiation is how do you differentiate this one? Is we can find this one by using the very basic property of differentiation. So it becomes this one times this one, and this one is 1 over y squared. And what about this one? This one is fx 1 over y. So it's actually 1 over y. And what's the PDF? PDF is 1. How we can find out that one is like because it's a uniform distributed. So the PDF of x in at place of 1 over y is just like it on anywhere else is 1. And yeah. And so what happened to 1 over y squared? So remember in this formula, this is only happened in y belongs to j, which is the transformation after j. So this is from 1 over y is in the set of 0 to 1 closed interval. So it's actually y greater or equal to 1. And it's become 0 if y is smaller than 1. So we have solved it. Cool. And we'll see one more example. And this example is a transformation from the normal standard normal distribution to another normal distribution with mean mu not 0 and standard deviation sigma, which is not 1. So it becomes more complex, and this can serve as a basics for solving other continuous differentiation or continuous CDF and the transformation over not standard normal distribution. So we will compute this one. So first compute x is equal to the sigma z plus mu. This is very simple. This is just get the result from here. And we want to define the function of transformation u on z. So it's like times sigma and plus u. So u inverse becomes this one. It's just like you put in the z on one side and compute what x makes z. All right. So differential of this one, x over sigma is 1 over sigma, and the little part is 0. So it's 1 over sigma. And apply the basic formula here to get fz, because the normal distribution is also the Gaussian distribution. We use the Gaussian distribution formula here. And this is 1 over sigma, which is we left behind. And just plug in x minus mu divided by sigma into the x position of the original Gaussian distribution. And we can do one more step to put the sigma into the root square. So this will be the result. So I think this is like a um it's a wonderful setup for the transformation. We see at least three different examples of how transformation and this formula works. So this leads us to the second topic of this lecture is the expectation and variance of continuous random variable. So first we'll see what's the expected value formula. So for discrete random variable, we have already talked about is expected value is in the form of this one. So it's a sum up of all px times x. But for continuous random variable, it's impossible to compute all of the px times x and square them out. So we use another average formula, average method, which we usually solve for of infinite sequence, um, if it's converged or not. So this is the integration. So the expected value of a continuous random variable x is defined as this is the PDF of x. We do the PDS times x and then do the integration to find out its expected value. And notice that this should be a definite integral instead of indefinite integral. It's right as a indefinite integral because the domain is not defined. But for um for confidence or for safety, we always write from negative infinity to infinity. But we know if it's like just going from 0 to 1 and all other parts 0, we can write as 0 to 1 as this example illustrates from 0 to 1. But we always write from negative infinity to infinity to make sure all the situations considered. Well, this is a very standard example of how to use it. It's just like we know the PDF of uniform distribution is 1 over b minus a, and times x to compute the integral to get the result. What's the expected value? So this is the expected value. Definitely, this is for the uniform distribution because it's a plus b divided by 2, which is give us a feeling of like the center point of in this uniform distribution, which is its expected value. And for this one, it might get more tedious about computing. So I'm not decided to compute it. It's very tedious, but the idea is the same. You just plug in value of x and times its PDF, which look like a little bit longer than what's the PDF here. And after several steps, you will get mu. And I will say one mysterious step is this step. So why this one go to 0? And why this one go to 1? I think I don't know what author writes it in this way. But for me, I think leaving this form is very okay because you get a value, and this is not necessary to get it. The computer can compute it successfully if you plug in. Yeah, one of the website I recommend for integral computing is called Symbol Lab. If you can use that to compute, you don't need to compute by hand. Use the technology wisely is quicker for solving probability questions. So one interesting application of transformation in the expected value is the transformation formula. Remember in the expected value for discrete random variables, we are using we say the gx times, if g is a transformation, then gx times fx, px, which is pmf, and sum it up is the expected value for transformation of gx. So it is very similar. It is very similar to the continuous version, which is gx times is PDF fx, and do the integration from negative infinity to infinity dx. And it has one prerequisite. Oh, yeah. So these have one prerequisite. So if we can calculate this expected value, we must make sure this one is absolutely convergent, which is like x, we take the absolute value of x and times the fx, the PDF is smaller than, it's not infinite, it's finite. It is bounded, but it's similar for this one. Because if it's go to infinity, what happens is the expected value goes to infinity as well. So in that case, it's possibly if the gx expected value is not defined. All right. So yeah. So if you're interested, you can look at the proof here, like how to prove it by integration. But we will see another interesting idea here, which is the variance. So we can make a summary of what we find before. So for the discrete variable to compute the mean or expected value is this form. The fx here is the PMF. And for variance, we know we can compute from like expected value of x squared minus x expected value of x squared. That's like a traditional way to compute it, but we can also compute the variance in this way. Because remember, variance is just a transformation of expected value. So the g function becomes x minus mu squared. This is a transformation. We can view it in that way as well. And standard deviation is just a root square of the variance. Okay, but for continuous random variable, mu is equal to from negative infinity to infinity integral with x times PDF dx. And in the same reasoning, the variance can also be viewed as the transformation of x, which is x minus mu squared. All right, so we just apply it in the transformations formula to get gx times fx and dx integrate by from negative infinity to infinity. So this one is also solved. So this is a typical formula we use for computing variance for continuous version. And standard deviation is the same. So let's see one more example. Maybe the first example we see is the uniform distribution AB. What's variance on it? So the variance on it is first we will compute the expected value we have as we done before, and we'll use the expectation to compute the variance. So the variance can be computed in this way as well. So this is the same as we do the discrete variable. So in this way, we compute as x squared times one b minus a over 1, and this compute also as this one. And for doing the expectation squared, a squared plus b squared plus 2ab divided by 2 squared, which is 4. And we minus all together, we get this as the result. All right. So remember, we do one interesting example of the not standard normal distribution before with the mean mu and the variance sigma square. So how can we do that? How can we compute this variance? We compute variance in the way we just defined before. We view it as a transformation. So this is the PDF, and the transformation is x minus mu squared. All right, so let's compute this form. So this form can be computed as actually it's very hard to compute. I must say it. So if we do the transformation of z is equal to like x is equal to sigma times z plus mu, then what change? What changes? This becomes z and sigma, and this is because minus mu is just minus out. Minus mu is minus out, so it's just sigma x, and sigma x squared is sigma z. So sigma z squared is this one. And here sigma z is here. And we just and this is just the first step. And moving from to next, we separate z into 2. And because sigma doesn't contain any terms of z, we just move it to the beginning. And this sigma is divided by this one successfully. So this can treat as a coefficient. And the next step is to the real computation of the integral. And yeah, and after that, we found, so how to compute this one is we use the integration by part. Probably we do the integration by part, so we treat this one as a dv, and this one is a u. So become this one, like uv minus d v du. And we found out later is this form. So again, think about how this one equal to 0 and this one equal to 1. And we made it down. And in the last minute, I want to introduce 2 important results of the when we are dealing with expectations and variance of transformation of random variables. So the first one is it's very easy to think about. If x is a random variable, both okay if it's discrete or continuous, then we are setting. Then if x absolute value to the power of p is smaller than infinite, then x to the power q is smaller than infinite. So this lemma 7.7 is this one is important for computing how to say, it's by like checking the assumption for doing the expectation. Because if it's not smaller than infinite value, if it's infinite, then we are not going to compute its expected value. So this is the case. And in this case, how to check like if q is smaller than infinite? It's just like if q is belong to the interval of 0 to p. So if it's from 0 to p, then it can be solved. Okay. And another useful result is lemma 7.8. And this one, well, this one is like we can narrow down the domain of the expectation. So remember, we always say like it's going from negative infinity to infinity. But in this case, we can narrow down to 0 to infinity. If that can helping us to make the computation easier. So there's 2 assumptions for it. The first one is x is a PDF with fx equal to 0 when x smaller than 0, which means like the PDF looks like form in this way. I will briefly write it. It's like if this is 0, then maybe it seems like this way. So smaller than 0, fx is always 0. So then it becomes like 1 minus fx from integrated from 0 to infinity. So we're gonna make a very simple proof about it. Let's see. Because and another assumption, it has 2 assumptions. Another assumption is fx have a defined CDF, which is already defined. We don't need to find another. If it's do not have a defined CDF, like it's only have a PDF and it's not like anti-differentiable, so it doesn't have a CDF. But we assume it has a CDF. So the CDF is fx. So first, how to prove it? We write the fx to become p x smaller or equal to x. And because 1 minus p x smaller or equal to x is the same way as we do the we do the converse. We do the converse like x greater than x. So this becomes p x greater than x. All right. So in this case, we say x belongs to x to infinity because this two terms is similar. And this form is still 0 go to infinity. And how to write this form? This is x go to infinity because the random variables is belong to this interval. So for making it more clear, we define y as a random variable instead of s, or if we become too many x there. So fx, fy, dy in the interval x to infinity, this is same as the CDF here, the CDF x greater than x. And after that, how we can do this one? This one can be viewed as 0 to infinity. And we just add an indicator function of y greater than x. So fx is equal to fy is equal to itself when y is greater than x, and fy is equal to 0 because the indication function becomes 0 when this condition not satisfied. So so it actually becomes x to infinity without this indicator function. And the next step, we just do the change. We just do the Frobenius rule. I remember there's a rule called Frobenius rule. For Frobenius rule, it's like we can do the transaction of the inner integral to the outer integral. So dx becomes inside, dy becomes outside, and we just compute this out. We just compute dx out. So it becomes 0 to, I think this is from x to infinity, fy dx dy. Oh, maybe it's like y to infinity. Yeah, it's y to infinity because the random variable is x. So y to infinity dx dy, and it becomes, after computing the x out, we find is actually in the form of a random variable in the form of an expected value y times the PDF of y dx 0 to infinity, and y, remember y is the same random variable as the capital X we changed here. So yeah, so that's the second result. So this result, this fact, we can say a useful fact, help us to narrow down the domain. So if a function looks like the fx is always smaller, it's always 0 when x smaller than 0, we can make it easier to compute its expected value by using CDF. And this useful fact help us to check the assumption for if we can actually compute the expectation. If so just use the powers ordering. All right. So I think that's all for today. Thank you for attending.